Hello again everybody. After the distraction of the Marconi 2380 spectrum analyzer blowing up and having to repair it, I thought we could get back to what we were doing previously, which was just playing with some RF test gear. And I think the main thing we were talking about is how not to blow up your test gear, how to connect various bits of test gear to transmitters or receivers, mainly transmitters, how you connect transmitters to things like spectrum analyzers and oscilloscopes without blowing them up. And I said that probably the best way to connect a transmitter to a spectrum analyzer is not to connect it at all. That's probably the best way. But let's look at some other types of connection and some other types of measurement. So this radio is an RT351, and well, I can almost hear the mirror mints being spat out and the Zimmer frames vibrating in anger by the VMARS crowd, because it's not actually probably correct to call it a 351, because this is the transceiver part here, but you see we've got something bolted in the middle here. Now this thing in the middle is a linear amplifier which gives it an output. It boosts the output from about 5 watts to around 20 watts, and then at the bottom end of the receiver you see we've got this enormous NiCad battery here, which is very heavy. In fact, the whole radio weighs an absolute ton, and whenever I get this out of the cupboard and play with it, I always think of my uncle who was in the Falklands, and I can just imagine the squaddies having to hump this across the landscape, maybe carrying some spare batteries. So let's talk about the main part here. This is the main part of the transceiver. And as I said, it's part of the Clansman suite. Now the Clansman radios were designed to replace an earlier version of radio that was used by the British Army, which was called the Larkspur. And I've got some Larkspur radios as well that maybe we'll look at some point. But this particular unit, as I said, it's a 351, and it was made by Raycal, although I think they may have been built under a licence by a few other companies, including Plessey and Mullard as well. So in many ways this radio was a little bit ahead of its time in that they were frequency synthesised radios. So what that basically means is they had these selector switches on the front, and you could tune these between about 30 megs and 30 megs and 76 megs, and they had a 25 kc channel spacing. So you didn't have, older radios that you might be used to. You'd have a VFO control, and you'd have to adjust that VFO and try and align it with the opposite station you were trying to communicate with. It was all a little bit fiddly, a bit hiss and miss. You could probably be close to the station and never hear them. But this is totally channelized. If you know the channel you want, you just set it on these large thumb wheels here, and Bob's your uncle. You can talk to people. I've got a coax cable plugged into it at the moment for taking some measurements, but normally the antenna would just clip onto here. It's a little bit of a bayonet fastening. So that's the frequency selection controls here. This is the on and off switch, if you like, and it's got a few different modes. So at the moment that's set to 0. Let me bring you in a bit closer. So let's have a quick look at this on and off control, and it's got written on it 0, W, L and a star. So at the moment it's got a 0 on it, and the 0 means I don't know if it's an O. It's probably an O rather than a 0. O means off anyway. So at the moment the transceiver's turned off. If we put it on the first click, it goes into what they call whisper mode. Whisper mode is to be used if you're behind enemy lines and you don't want to be discovered. So this is a typically the handset you might use with one of these radios. It's just like a telephone receiver. So when you put this into whisper mode, it turns the volume down on the speaker, so that if anybody's walking past you, they're not going to hear the radio signal that you're receiving from one of your colleagues. So it turns the volume down so nobody can hear you. The other thing it does, it turns the microphone volume up. It sets it to maximum, so that if you're talking very quietly, I don't know if you can hear that, so if you are talking very quietly, it will boost your own voice so you go undiscovered, so people can't hear you if they're walking past you. So that's okay when you're behind enemy lines and you're undercover. At the opposite end of the scale, when you're actually in battle, there might be all these explosions and bullets whizzing over your head and people shouting and screaming. You need to be able to hear what people are telling you, so you want to set it to maximum volume. So that's what this L setting is for here, which means loud. So we put it on L setting, it boosts the earphone, if you like, to maximum volume. What it also does, though, it reduces the microphone to minimum sensitivity, because you don't want to deafen the people at the other end by the sound of the battle. So it reduces the volume of the of the microphone, because I guess what tends to happen as well, if you are in battle and you know, you probably have a tendency to start shouting as well, so that it turns the microphone down. And then you've got a star here, which is the equivalent of turning the squelch. It's kind of a squelch. It's squelch at the moment, so I'll put a star on, and hopefully you can hear that. So that's just basically raise the squelch so we can hear anything. So when it's in loud or whisper, the squelches are set to preset levels, so the radio operates quietly. But if you just want to, I don't know, hold the squelch open, listening for a very faint signal, I guess, you can do that just by putting it on the star. So if you want to make the radio transmit, well, it depends whether you're using headphones or this type of telephone receiver, but this is the PTT here. So you just squeeze this, and it will start to transmit. And depending on what the output power is you want to transmit, you could use this radio standalone. In the standalone mode like this, with the RF energy coming out of this socket here, you'd be doing about 5 watts, which, you know, probably wouldn't go very far. There's a little connecting cable which you can put between this RF output socket and the linear amplifier here, and then you connect a separate aerial to here. So this linear amplifier is just a booster, and with that in circuit you can transmit up to 20 watts. One of the problems these radios, I think, would say that they suffered from was poor selectivity. So there was another unit that you had to bolt on the top of here, which they used to call a surf unit, which I think it was called selective something or other. Basically, if you had adjacent stations, they could overload the front end of the receiver, and basically everything would be distorted, and you couldn't pick stuff up. So you had to have a separate antenna unit, this surf unit, which is basically a variable filter, and you would have to set that to the frequency you want. So they had a lot of good things about them, but they had I would say that they had a lot of bad things about them, but I'm guessing they were very ahead of the time. So hopefully you found that interesting, but the main thing I actually wanted to talk about today is how we connect a transmitter to something like a spectrum analyzer or an oscilloscope. And in the previous video we looked at some ways of doing that. In fact, what I was using at that time was a large attenuator. Let's have a look at another way we could do it. So here's our Raycal watt meter, Raycal Dana, that we looked at last time. It's got a 10 watt range and a 30 watt range. Well, we've got it on the 10 watt range at the moment. So I'm just going to key up the transceiver, and hopefully that needle will go up. And there you go, we're on the top scale, 5 watts. So you can see there, we're looking at the input socket on the spectrum analyzer, and it says 0.5 watts max, and that's actually quite a high level for spectrum analyzers. It could be a tiny fraction of that. Now if we were to connect our 5 watt transmitter to that input, it's quite likely it would damage the input to the spectrum analyzer. Now this Marconi unit I use, it's actually very well protected. It's got a protection circuit built in. You never want to connect a transmitter directly to the front end of a spectrum analyzer. It's a bad idea. You will blow up your spectrum analyzer and you will cry, because they're expensive instruments to destroy. So having scared you to death about the dangers of connecting transmitters to your spectrum analyzer or oscilloscope, I'm going to show you another way you can do it. Last time we were looking at big banks of attenuators. Well, attenuators are expensive, and you need an attenuator that's capable of handling the power, and that will make it a big attenuator. It'll probably make it expensive as well. So I'm going to show you a really cheap way of doing it. Some of you might recognise this. What it actually is, it's a dummy load, and it's been modified by myself into what you might call, well, you call it an RF sampler. So I've built a sampling port on it which will take a small proportion of the radio signal and send it to the spectrum analyzer, and it'll provide a much reduced output. So the main input here, this is where we connect the transmitter to, and this one's rated up to 300 watts. I don't think it'll last long at 300 watts, but that's what it's rated to. So what we'll be able to do is we'll be able to put up to 300 watts into this dummy load, and we'll just get a tiny proportion of that 300 watts out of here, and the signal will be attenuated at a level that, fingers crossed, we're not going to blow up our spectrum analyzer. You can pick up dummy loads like this or very similar quite cheaply on eBay. This is an MFJ model, MFJ 260C, MFJ 260C is the model number. But there's lots like this or similar, And of course, one of the first projects that any radio amateur should probably have a go at is building their own dummy loads, because they're easy to build and they're a good little fun construction project. Buy your own resistors, build yourself a dummy load, put some connectors on it, and you can put a little RF sampling port on the side of it like I've done. So we'll look at that in a second. Well, we're going to connect the spectrum analyzer itself to the sampling port, so let's screw that into there. And again, I'm using N-type connectors. Typically I use a lot of BNCs in here, but I put an N-type connector on it because that's natively what the spectrum analyzer uses. That's an N-type on it as well. And I've also noted at the moment I'm breaking one of my cardinal rules, which is always have your spectrum analyzer with an attenuator on it. So I'm going to screw one on. And of course we like 10 dBs of attenuation because 10 dBs is 10. So that's going to divide our signal down by 10. So I'm going to disconnect our transmitter from our absorption watt meter, and I'm going to put it into our RF sampler because it's a dummy load, but what it's actually doing, we're using it as an RF sampler, so I'm going to call it an RF sampler. I'm just going to screw up some of these connections because they're a bit loose. That's okay. So we've got our dummy load plugged in, we've got our spectrum analyzer plugged in. Let's switch on our transmitter. It is on. So let's key up our transmitter and hopefully the spectrum analyzer won't explode. And there we go. You can see about in the middle of the screen we've got a signal appeared, and it's somewhere between -50 and -60 dBm. Just to keep the numbers straight and easy to work with, we're going to call it -50 dBm. And of course anybody who can work in dBm will know that that's about, well not about, it is, that's 0.1 microwatt. So we're transmitting 5 watts, which is the equivalent of saying plus 37 dBm, and we're actually only receiving -50 dBm or 0.01 milliwatt. We've managed to take a sample of our RF power. Most of the power has gone straight into the dummy load. It hasn't gone anywhere near the spectrum analyzer, and we've just taken a massively divided down portion of that signal and fed it to the spectrum analyzer. So let's just have a look inside our sampler, our dummy load, and see how that works. So I'm sure lots of you, we've all played with CBs and stuff like that in the past, or certainly a lot of us did, and most of us probably would have had a dummy load. So this is a dummy load. I've just taken the cover of it, and what's inside here is actually just a big carbon resistor, and there's actually a shield around this resistor, and I'm guessing the main purpose of that shield is maybe to maintain some form of constant impedance. It may be for screening, and it may be to stop you burning yourself on it, but I'm guessing the main function is actually to keep the impedance honest. Nothing very exciting about that, it's just a resistor. I said that what we were going to do is we're going to feed out a fraction of the power that's absorbed by the dummy load. We're going to feed it out to the spectrum analyzer, and the way we do that is really very simple. All I've actually done is I've got an N-type connector there, and I've drilled a hole through the case, bolted it on, and I've got a 50 ohm resistor. So on the centre pin of the N-type connector I put one leg of a 50 ohm resistor, and the other side of the resistor I've just got it grounded out on the chassis. And what it's actually doing is it's acting as a little antenna. It's sniffing, it's picking up a tiny proportion of the signal which is being absorbed by the dummy load. It's just picking it up, and it's coming out of the N-type socket, and that's what we feed into the spectrum analyzer. And I'm using a 50 ohm resistor here because it just presents a nice fixed impedance to the spectrum analyzer. Most frequencies it'll probably work without it anyway. Depending how you build this, you can actually set the amount of power that you send to your spectrum analyzer. Let me bring you in so you can see inside here a bit closer. The amount of power that you pick up, the amount of power that you sample, is kind of proportional to the size of the loop. If you want to pick up a lot of power, you would make the loop go into the centre pin of the N-type connector. You would put a long piece of wire that would pick up a large sample of RF energy, but you only want to take a tiny part of that power, then you just put a small loop in there, and I've got quite a small loop. And the other thing you might want to do is, if you want to pick up more power, you can move the loop closer to the dummy load. If you want to pick up less power, you move it further away again. So you've got lots of ways of adjusting the sampling power. Now, one thing about this little sampling unit, it isn't actually calibrated, and you will find, depending on what frequency you use it at, and I'm talking about extremes of frequency, the sampling port may be more responsive at some frequencies than others. It's generally not that important. I mean, I tend to work in the kind of the HF regions. If you were using this in the gigahertz, well, it wouldn't work very well. But if we're working, I don't know, anywhere between, I don't know, a few megahertz and a few hundred megahertz, anything between a megahertz and a few hundred megahertz, it doesn't matter too much. Having exact calibration for the attenuation factor isn't that important, or it isn't that important for me. Usually what I'm trying to do is I'm trying to compare the amplitude of two signals. One of the common things you might use this for is maybe comparing the output of the transmitter. So what you might want to do, for example, you would want to look at the output power of the transmitter, and then you would want to sweep the band using the spectrum analyzer, and you would want to look at the second and third harmonics. And what you really want to know is you want to know that they're well down on the centre frequency. But you could calibrate it. I mean, if you've got a transmitter or a signal generator which is fairly accurate in terms of output, you could calibrate it, and you could certainly calibrate it at the frequency ranges you're working at. Okay, well, just for giggles, I've actually disconnected the low power output from the RT351, and the low power output, I've now got it redirected. It's going into this linear amplifier, and in theory we're going to be getting about 20 watts out of here, so we could just check that. On a good day it'll do 20 watts, maybe our batteries are going a bit flat. Okay, so let's feed the 20 watts into our spectrum analyzer. Again, hope it doesn't go poof. And you can actually see now some distortion products. We've got a second and third harmonic there. So there's our carrier, and that's at 39 dBm. We've got our second harmonic, which is down quite a bit. That's at 74 dBm. And then we've got our third harmonic, which is down at 85 dBm. So you can see, for example, the second harmonic is minus 35 dBs down on the first, and then the third harmonic is minus 45 dBs down. I'm not exactly sure I can give you a hard and fast figure for what the difference should be between the carrier and the second and third harmonics, but I think a figure that I would be looking for is at least 40 dB. So you want, for example, this one here, the second harmonic, you really want this one to be at least 40 dBs down, lower than the carrier. When we were actually looking at our 20 watts being transmitted in the watt meter, what might not be clear to everybody, and it's kind of an interesting thing. Of course, you think that 20 watts is going into your carrier there, but there's actually a proportion of power going into your second harmonic and your third harmonic, and these are totally wasted. You know, the person at the other end of the line, if you like, the person you're trying to talk to, he's not tuned into the second and third harmonics. Well, hopefully he's not. he's trying to listen to you on the carrier. So it's interesting that, you know, our transmitter is wasting some of that 20 watts. It's putting it into these harmonic products, and that's doing nothing useful for us. Well, just to finish with, I just thought I'd show you a little kind of a dodgy trick. It's another way that you can make a simple RF sampling head. So what we've got here, we've got a BNC. It's a BNC T-piece. I'm sure you've seen them before. So I've got the transmitter connected to one side of the BNC T-piece. I've got the dummy load, which is an absorption watt meter in this case, that's connected to the other side of the T-piece. And then in the middle of the T, we've got our spectrum analyzer connected. So what I'm going to do is I'm going to key up the transmitter, and we'll just see what power we're transmitting. So I'll just key that up. So hopefully you can see that. That's 5.5 watts, just under 6 watts. Now I'm sure what some of you hopefully will be thinking, well, this is just a T-piece, is all that RF energy, some of it's going to be going into the watt meter, but surely it's just a T-piece. Some of that power is going to be going up this centre section of the T-piece, down the central leg, and that 5 watts or 6 watts is going to be going straight into the front end of his spectrum analyzer and blowing it up. Well, there's some shenanigans going on here, and let me show you what I've done. So here's our BNC T-piece, and it looks like a standard T-piece, but what the shenanigans is, if we actually fold it over, I don't know if you can you see into there with the camera? Hopefully you can see that the centre pin has been removed. What I actually did was I took an electric drill and I put it in the central of the barrel of this just and ran it, and I destroyed the centre pin, and I actually kept going with the drill and actually drilled just a little bit into the body, because some of these are manufactured differently, but there tends to be quite a lot of metal, and they're filled with a plastic sleeve, so I've actually drilled in a little bit of depth there. So this central leg, so when we're connecting our normal connector that goes to the analyzer, this has got a pin on it, but the pin isn't making contact with anything. There's actually an air gap between this BNC pin and the bit of exposed copper. Hopefully you can see in there. You can see that you can just see a little bit of like gold material there. Well, that's just a flat surface. So the RF is coming out of that flat surface there, and it's capacitively coupling with the pin inside this BNC cable here. So there's no physical connection, that's what I'm trying to say. So all the coupling between this sampling head and the spectrum analyzer, it's just being done by capacitance. So there's a really cheap and nasty way to make a sampling tee. Now you've obviously got to be really careful using these, because if you pick up a standard one and plug it in like I nearly did earlier, you're going to blow up your spectrum analyzer. So I'm really going to go back and say what I did in the beginning. You've got to be ever so careful when you're connecting things like transmitters to your spectrum analyzer. It's something which is best avoided, and you can avoid it, as I say, 99 times out of 10. Probably the best way to do it is just use some form of sniffing aerial, or maybe build something like this. I think this is a relative safe way of making a connection. But when you do it for the first time, don't go connecting, a 100 kilowatt transmitter to it. What you want to do is you want to find a very low powered transmitter, or even a signal generator, and just send a few milliwatts through, just a few milliwatts, because you can test these things. You don't have to test these things at watts, you can test it at milliwatts. So send a very, very, very small signal through it, figure out what the attenuation factor is, and maybe write it down on the bottom, which is what I should do, and then you will know that you can plug things in with relative safety. Now I know a lot of people watching probably won't have a spectrum analyzer, let alone 2 or 3 of them like I have. I'm lucky. But what you probably have is an oscilloscope, so you can just see here, rather than connecting the input to the spectrum analyzer from the sampler, we've actually just connected it into our oscilloscope. So let's just key up the transmitter, and you can see there we're transmitting on 70 megahertz, and it says on the display 70.45, and you can see quite a nice sine wave there, can't you? Well, I've got absolutely no doubt that some of you RF perverts out there will want to see me going in taters deep with 100 watts of Italian QRP, so let's just give that a go. So we're transmitting 100 watts there, and another way of saying 100 watts is plus 50 dBm. Now if you look at the markers that we've got set up, it says that the markers, I'm going to round it up, it says minus 50 dBm. So we've gone from plus 50, 100 watts, to minus 50 dBm. Now in terms of milliwatts, what that actually means is the spectrum analyzer front end, it's seeing 0.000005 watts. So you can see that our attenuator is actually really conservative. If anything, I've probably got more attenuation than I want in this device, but it's very easy to adjust it. All you've got to do is you've got to open up the box. You can either make the area of that loop antenna a little bit bigger, that little loop wire, you can either just make that loop a little bit larger. Alternatively, you can take the wire and bend it closer to the dummy load, and that will reduce the attenuation factor. So you've got a little bit to go at there, but it's probably better to start off conservatively. Well, we've been transmitting there for, I don't know, a minute or so, and these transceivers aren't really rated to be doing 100 watts on FM. Obviously they'd be much happier on SSB, where you're only actually seeing any power being developed on your speech peaks and stuff like that. So it's not a good idea to keep your transceiver keyed up very long at these high powers, and especially when it's switched into FM. But this dummy load is doing its job, because it's actually now getting quite hot to the touch. It's certainly warmed up, it's well above ambient, but it's doing its job. This is converting all that RF energy into heat, and we're just getting a smidgen, a wee soup song even, and that's been fed to the spectrum analyzer, and that was the idea of today.